So Bernoulli's equation really puts all of this together. It puts the ideas of external pressure, flow rate, and energy due to height into one equation. And essentially what we have is this. We have a pipe. On the left end, we have a certain area, a certain speed, and a certain height. And on the right side, we have a certain area, a certain speed, and then a different height. And what Bernoulli's equation says is that if we take the left-hand side, if we take the atmospheric pressure, or the pressure, the external pressure, then if we add the pressure due to the flow rate, so this is pressure due to flow rate, and then rho GH is pressure due to depth. That because of conservation of energy, that should be the same as what we see on the other side, on this side of the pipe. This would be atmospheric pressure over here on the right, pressure due to flow rate on the right, our velocity on the right, and then pressure due to height on the right. It's interesting when you look at this equation, it looks a lot like energy. And that is not a coincidence. This really is a statement of conservation of energy. But instead of using mass, we are using density, which is a very similar measure. That for that pipe, that on the pressure on the left-hand side could be written like this. And on the right, similar expression. And now what I'd like to do is I would like to subtract the left side from the right side. So if I subtracted all of this, if I do it to the left side, then I have to do it to the right. And then what I would end up with is 0 equals P2 minus P1 plus 1/2 rho V2 squared minus 1/2 rho V1 squared plus rho G H2 minus rho G H1. And a couple of more adjustments. If I subtract P2 minus P1 from both sides, I end up with this. 1/2 rho times V2 minus V1 squared plus rho G H2 minus H1. This form of Bernoulli's equation is much more useful in problem solving. So I'm going to try to remember this and hang on to it for my next example. Speaking of my next example, a water tank has a spigot near its bottom. If the top of the tank is open to the atmosphere, determine the speed at which the water leaves the spigot when the water level is 1/2 meter above the spigot. Okay, in order to solve this problem, I'm going to have to make some assumptions. And the first assumption that I'm going to make is that P1 and P2 are the same. Or here I've written it as PT, the pressure at the top, and the pressure at the hole are the same. Because basically the atmospheric pressure is pushing in on the water both at the top, atmospheric pressure is pushing in here, everywhere, and atmospheric pressure is also pushing in here. And atmospheric pressure does not change very much in 1/2 meter. That's just not a very big difference. So I'm going to go ahead and assume that all three of these are the same. The next thing that I'm going to assume is that the velocity of the water at the top is very small. If this spigot is small and is just letting a trickle of water out or a stream of water out, and if this is a very large tank, then the water level will go down very, very, very slowly. So the velocity of the water at the top will be essentially 0. So when we're working with Bernoulli's equation, we want to check our assumptions. Do we have a huge tank of water relative to a tiny hole? Does that mean that the water level is going down very, very slowly? Is the tank open to the atmosphere? That means that the pressure, the external pressure, is the same. And the last thing we want to think about is that the system is being evaluated only for the moment that the values are given. We recognize that over time the tank will drain and the velocity of the water will change. But I'm not going to worry about that. I'm going to worry about trying to solve it for this instant in time. So here we go. Using Bernoulli's equation, I'll write this out. Oops. So H2 minus H1, that's basically your change in height from the top to the bottom. And that was 0.5 meters. Okay. So I'm going to call this P2, and over here I'm going to call P1, and this is going to be velocity 2, and this is going to be velocity 1, and this is going to be H2, and this is going to be H1. So first of all, the change in these pressures, these atmospheric pressures, is 0. There's really no change. The density of water is 1,000. The velocity at the top of the tank, we said we're going to assume is 0. The velocity at the bottom of the tank is what we would like. Again, density is 1,000, G is 9.81, and then the change in height is negative 0.5. So I go through and I solve this. I have 500 b squared equals whatever this is, 500 times 9.81. And when I solve that, I get that the velocity is 3.13 meters per second.